I thought I'd do a couple examples, more examples on angular momentum, because I think it's something that's very challenging in this course, and it's useful to sort of look at a set of problems. Not much can be. So I'm going to do about 3 problems here. Well, I'm going to do 3 problems. And the other thing I'm going to do is one which is going to be a bit different, and I'm going to use a vector approach. So I think it's helpful a little bit now, but it'll be more helpful in the next chapter when we start dealing with rigid body kinematics and later on with kinetics. I have a box of mass m, and it's traveling down a smooth circular ramp. So that's a thin blue line, such that when it hits the angle theta, it has a speed v. Determine its angular momentum about point O, and point O should be on the diagram, but here it is. There. At this instant, and acceleration tangential. So you have the mass. It's coming down at some angle. You define in there the normal and tangential directions in and t. You have the theta that you were given at the problem at the beginning. You're just flipping it around. You have weight acting downward, and you have a normal force from the slide onto the mass. This is the mass, of course. The angular momentum is just going to be h naught, about 0, rmv. And in this case, the only thing causing any type of moment is going to be the weight. So it's mg r sine theta. Mg acts downward, the moment arm is over here. And that is going to be the rate of change of angular momentum. Since both r and the mass are constant, I can write that as dv dt. And since this is sliding down a ramp, if I calculate it, I'll find it's g sine theta. Here's a second one. The 2 kilogram disc rests on a smooth horizontal surface and is attached to an elastic cord. So this is the elastic cord here. It has a thickness of the cord, or a spring constant of the cord, which is 20 newtons per meter, and is initially unstretched. If the disc is given a velocity initial of 1.5 meters per second and is perpendicular to that cord, determine the rate at which the cord is being stretched and the speed of the disc at the instant the cord is stretched by 0.2 meters. So it starts out at 0.5 meters here. You know that it is initially unstretched, so you're going to expect to see a stretching to about 0.7 meters. So, coordinate system. You have the mass, and it travels along some curve at 0.5 meters and 0.7 meters. So if I sort of do all of the force on the cord pulling inward, I have weight acting downwards, I have the normal on the disc, I'm going to have one velocity I'll calculate directly from the momentum and one that's coming out of energy. So from conservation of angular momentum, I have R1 md Vd1 and R2 md Vd2 mom. Substitute in the numbers, and I get the final velocity of the disk at 1.07 meters per second. Now, at the other end, this is a system that is conservative. There's no friction applied to this system, and the terms that are sort of playing a role aren't doing very much. I've got initial kinetic energy. I have initial potential energy, which is 0 of the spring. I have final kinetic energy, which I don't know. And I have the final stretch of the spring, which is 1/2 kcx squared. And I get a velocity d at 0.2, total velocity of 1.36 meters per second. Now, since it's conserved, and this is a conservative system, I can calculate the final velocity as being a combination of both the tangential velocity and, well, sorry, I'm not going to call it tangential velocity, one component of velocity along the curved path and the other that's sort of stretching along the chord. And so in that case, I get an additional component, which is 0.838 meters per second from the total energy of the system. Finally, this one is not a tough one, but okay. It's determine the total angular momentum for the system of 3 particles about 0.0. All the particles are moving in the xy plane. So here's the xy plane. I have some lines here that become more clear in a second. I have mass of A, mass of B, mass of C. Each of those has a velocity. Velocity of A and C are both negative along the y-axis, and velocity B is also negative but along the x-axis. You have all of the masses here, and you are given a set of positions. So A is 900 millimeters, it's positive as it moves along the positive x-axis. B is 700 millimeters, it's also positive, again, same reason. C is positive, same reason, and it's 600 millimeters. D and E are both negative. D is 800 millimeters, and E is minus, or 200 millimeters, both, again, negative. I'm going to do a slightly different approach. You know that from the standard definition that I can sort of calculate for a system of particles all of the angular momenta for each of the components. So H naught is really H of A, the angular momentum of A about O, angular momentum of B about O, and the angular momentum about C about O. And I can write that as RA cross MAVA RB with respect to O cross MBVB RC with respect to O cross MCVC. Everything is defined with respect to that. So I got A 0, 0, 0 MAVA because this is in the J component, CB 0, MB, which is the only one acting in X, 0, 0, DE, and 0 MCVC. So the linear momentum on the right, there you go, and the position with respect to O on the left. And I'm just adding all the terms up. I have all of the expressions here, and I have all of the terms here. From this, I'll get a final H naught of 12.5 Newton meter second in the K direction, which isn't a surprise since this is all occurring in the XY plane. I expect that the rotation will be about the Z axis, or K. Angular momentum is a very hard quantity to visualize, and it's often more difficult than people sort of give credit to it. And intuition, especially at this stage, is often very unhelpful. Vector approaches often are helpful to sort of start to learn how things work and sort of understand why the motion occurs the way it does. This is a challenging concept in the course, and the only goal here is to create examples that help a bit.